Whenever the water sides of a boiler have been opened, it must be inspected, closed, and hydrostatically tested before being placed back in service. Inspect all drums and headers for loose gear. Also, be sure they are clear of personnel. All the internal steam drum fittings must be reinstalled. First, the internal feed pipe, then the de-superheater, next the dry pipe, and finally the steam baffles. You are now ready to reinstall the handhole plates. The boiler cannot operate properly unless all pressure parts of the manhole and handhole plates are thoroughly tight. Here are the cleaning tools you will need: a hand wire brush, a hand scraper, fine emery cloth, thread dyes, and a wrench. The gasket seating surfaces on both the plate itself and the header or drum must be thoroughly clean. Brush the plate with a hand wire brush until it is clean of all rust and scale. Be sure to give particular care to the threads and gasket seat. After brushing, polish the seat with emery cloth. Next, oil the threads. Then, with a die nut, rechase the threads on the plate stud. Now, brush the seat of the header with a short-handled wire brush. If necessary, polish the seat of the header, taking care, however, not to dig into the seat. Then, using a flashlight and a hand mirror, inspect the seat of the header for any bits of the old gasket remaining on the seat. Now install the new gasket on the seat of the plate. Be sure the fit is right, not too loose, and not overhanging the edges of the plate. Using an open-end wrench, set up the nut lightly, just enough to hold the plate in position. A light tap will help the plate to seat firmly. When installing the round handhole plugs found in superheater and economizer headers, special assembly techniques are often required. Follow the procedures in the manufacturer's instruction books. Our third and last step in closing the boiler, installation of the manhole plates. These plates are installed in practically the same manner as the handhole plates. Care must be taken to clean all gasket seats thoroughly on both manhole and manhole plate sides. With both seats cleaned, install the gasket on the plate. Then set the plate in the manhole. Set the arch bars in place. Thread on the nuts and tighten lightly. Then center the manhole plate accurately in the manhole opening. The clearance between the opening and the shoulder in the manhole plate should not exceed 1/16 of an inch all around. If excessive clearance exists, report it. With the boiler closed, it is now ready for hydrostatic testing. As the pressure is applied, the gaskets will be forced into place by the surrounding water pressure. However, if a plate has not been properly seated, it will continue to leak. In that event, a slight blow with a hammer may relieve the tension on the gasket, the water pressure behind the gasket forcing it into place. As the hydrostatic test is run in the boiler, look for leaking plugs, a condition usually caused by the presence of foreign matter or by small nicks in the gasket. In such a situation, the leakage can be corrected only by breaking down the fitting, removing it from the header, and re-cleaning or replacing the necessary parts. By doing the cleaning job right when installing handhole plugs, you will avoid the necessity of redoing the job. When all leaking gaskets have been adjusted, set up the plates firmly using a handhole or manhole plate wrench, especially designed for the job. The successful hydrostatic test proves that the boiler has been properly closed and is ready to be put back in service.
Boiler damage caused by scale can cripple your ship. To prevent this, boiler water must be periodically tested to determine its condition. The basis for all boiler water testing is the water sample. If it has not been properly obtained and is not representative of the water in the boiler, test results will not reflect the true condition of the boiler water. In this film, you will see how to take a boiler water sample. Although it is possible to obtain a boiler water sample from a number of locations, a sample taken from the water drum is the most representative of the water in the boiler. A boiler water sample cooler is placed on a line which is connected to the blowdown line from the water drum. A second sample cooler, used for de-superheater leak testing, is located on a line connected to the de-superheater outlet. Sampling procedures are the same for both. There are at least 2 valves located before the sample cooler. A sample line exit valve is located after the sample cooler. Cooling water, usually salt water, is valved both in and out of the cooler. In taking a boiler water sample, the coolant must be activated prior to sample flow. If it is not, the high temperature of the sample could severely burn you. First, make sure the cooling water exit valve is fully open. Then start a full flow of salt water coolant through the cooler. Starting with the water drum, open all valves between the drum and the cooler. Fully open the cooler's sample line exit valve. Let the sample flow until it flashes to steam. When the sample flow has flashed to steam, throttle the sample line exit valve until a liquid flow is obtained. Let the water flow until its temperature is less than 100 degrees Fahrenheit. Usually, this will take at least 5 minutes. When the sample temperature is less than 100 degrees, rinse the quart plastic sample bottle several times with some of the sample. Then collect a full bottle of sample. Cap the bottle to prevent particles from dropping into the sample and to minimize exposure to air. Once the sample has been collected, it must be tested within 30 minutes for accurate test results. To secure from sampling, first, close all valves on the sample line, starting with the valve closest to the water drum and working out to the sample exit valve. Finally, secure the coolant inlet valve. The cooling water outlet valve should be left open. The frequency of boiler water sampling is determined by the status of the boiler. For a boiler that has been freshly filled and treated, sampling is performed when the boiler is placed on the line and continued until test results are within limits. In the case of a steaming boiler, sampling must be performed daily, before and after any water treatment, prior to securing, and whenever unusual conditions arise. In the case of an idle boiler, under wet layup, sampling is performed prior to light-off. For an idle boiler under wet layup using a steam blanket, sampling must be performed prior to light-off, after any water treatment, but at least weekly. Remember, for test results to reflect the true condition of boiler water, the water sample must be obtained from the correct location, using the proper procedures, and at the specified time.
The deposit in this boiler tube was caused by solids in the boiler water, a condition caused by seawater contamination. To prevent this, the chloride content of boiler water must never exceed prescribed limits. Therefore, both boiler water and feed water must be tested at specified intervals. In this film, you will perform the chloride test. The procedure is the same for both boiler water and feed water. First, prepare the 3 reagents used in the test: chloride indicator, nitric acid, and mercuric nitrate. Chloride indicator is stocked in capsule form to prevent deterioration. To prepare the chloride indicator, empty the contents of a single capsule into the chloride indicator dropping bottle. Next, add 50 milliliters of 95% ethyl alcohol or isopropyl alcohol. Place the stopper in the bottle and shake to dissolve the contents. To prepare the nitric acid reagent, transfer 50 milliliters of stock nitric acid to the reagent bottle. Add distilled water to the mark and mix contents. Place the burette assembly on the reagent bottle and pump up the burette. Follow the same procedure to prepare the mercuric nitrate reagent. Transfer 50 milliliters of stock mercuric nitrate to the reagent bottle. Add distilled water to the mark and mix the contents. Place the burette assembly on the reagent bottle. Pump up the burette. Drain a little solution to be sure the burette tip is full. Then pump the burette back to zero. You are now ready to run the test itself, in this instance on boiler water. Use a clean plastic bottle to draw a sample of water. Let the water flow freely from the sampling connection to clear it of stagnant water and sediment before you take a sample. Measure out 25 milliliters of water and place it in a clean casserole. Add 5 drops of the chloride indicator. The sample will change to a blue-violet or deep red color. Now add the nitric acid carefully as you stir the contents. Continue this process until the blue-violet or deep red color changes to yellow. Then add exactly 1 milliliter of nitric acid to obtain the proper acidity. You are now ready to start the mercuric nitrate titration. Stir the solution and add mercuric nitrate until the casserole contents just change to a blue-violet color. A faint blue color will first appear. Do not mistake this for the blue-violet color. Read the burette, 0.6 milliliters, and log the quantity used. The amount of mercuric nitrate used is equal to the chloride content of the water in EPM. For testing feed water, the procedures are identical with the boiler water test, except a 100 milliliter sample is used. Because the volume is 4 times as large, the mercuric nitrate used must be multiplied by 0.25. This equals the chloride content in EPM. Blow down the boiler if the chloride content exceeds the maximum allowable limit. Accurate testing requires proper care of the test cabinet. Before and after every use, clean each piece of equipment thoroughly. To check the accuracy of the reagent, use the standard solution supplied for this purpose. Only by careful performance of the test procedure and proper care of the equipment can you obtain the necessary accuracy in the chloride test.
This diagram represents, in a general way, the several types of vapor compression distilling units used by small surface ships and by submarines to distill fresh water from seawater. There are 3 main components: an evaporator where seawater is boiled and the vapor condensed to make distilled water, a compressor, electrically driven, which generates heat by compressing the water vapor, and a heat exchanger which uses hot liquid discharges to preheat incoming seawater.
Heat exchangers and compressors are fairly common, so they'll not be described here. Evaporators are less familiar. This is an actual evaporator cut away to show its interior. For our purpose, this crowded arrangement of chambers and tubes will be shown like this. All essential features are represented. Note the 4 chambers, that chambers 1 and 3 are connected by tubes, and that chamber 2 is connected to the compressor and to chamber 4. Only 4 tubes are shown here, but actually there are several hundred. This film shows in general how vapor compression distilling units work and how to operate them. For precise information about any particular type, consult the appropriate technical manual. In an operating unit, many things are happening at the same time, and so we'll have to look at it in parts. Therefore, how a unit works will be described under 3 headings: the flow system, the heat transfer system, and the control system. The flow system traces the movement of fluid and shows in a general way what happens to it. Flow starts with seawater pumped through the heat exchanger into the evaporator. It pours through a downcomer, rises through tubes, where it comes to boiling and enters the top chamber. Here, the flow divides. Following one path, some of the boiling seawater spills into the brine overflow to carry away much of the scale-forming sea salts that otherwise would soon clog the evaporator. The hot brine flows through the heat exchanger and goes overboard. Following the other path, water vapor, produced by the boiling, passes through baffles to remove any salt-laden drops, and then goes through the compressor. To distinguish between the initial vapor and compressed vapor, we'll call the compressed vapor steam from now on. The steam flows down into the next lower chamber and condenses on the tubes as distilled water. The hot distilled water drains to the bottom chamber, passes through the heat exchanger, and then goes to storage tanks. In surface ships, pumps move the discharges. In submarines, gravity flow moves the discharges. The brine collects in a tank, and at intervals, compressed air blows it overboard. In a similar manner, the distilled water collects in another tank and is blown to storage. The method of handling the discharges is the only difference between submarine and surface ship units. Otherwise, operation is basically the same for both. This concludes the description of the flow system. In the heat transfer system, you'll see where the heat comes from and how it maintains boiling. There are 2 heat sources: the compressor, which is the main source, and electric immersion heaters. For starting, the immersion heaters boil the distilled water, filling these spaces with hot vapor. This vapor, in turn, boils the seawater, producing vapor in the upper chamber. When water changes to vapor, the vapor absorbs the large quantities of heat that cause the change. In an operating unit, the hot vapor passes through the compressor. Compression generates additional heat. Condensation releases the heat that caused the vapor. There's also the heat acquired during compression and the heat acquired before the actual boiling started. Of the total heat, some transfers to seawater in the tubes. Some heat, carried off by the hot discharges, transfers to the seawater passing through the heat exchanger. The heat transferred at the heat exchanger and at the tubes boils the seawater, passes to the resulting vapor, and by way of the steam, returns to boil more water. Thus, there's a continuous heat cycle from seawater to vapor to steam, back to seawater, and so on. Most of the available heat is used for boiling, but some heat is lost by way of the warm discharges leaving the heat exchanger, and some heat is lost through radiation. When the compressor cannot supply enough heat, additional heat is provided by the immersion heaters, which turn on or off as they are needed. The control system includes all the devices for controlling unit operation. The control system also includes the indicators which reveal conditions within the unit. Two controls are for maintaining vapor temperature. One, a seawater feed valve, which regulates seawater feed rate. And the other, a means of manually switching one or more heaters into the heater circuit to regulate heater input. There are two pressure gauges which serve as temperature indicators.